Hello students, in the previous session we discussed about dielectrics and we understood that how a dielectric behave when it is put in an electric field. And today we are going to understand what the local field of an atom means. Now when a dielectric is kept in an electric field, you know that it will experience a total effective field because of several things. Because when you apply a field, charges get separated within a dielectric, so that will obviously make another field. And there is a macroscopic field existing on the whole specimen. Effective field exists appearing on the whole total of the volume of the specimen. But actually, if you consider an atom within a dielectric, okay, so the atom within a dielectric actually experience a field different from the total macroscopic field of the bulk material. So today we are going to understand what is the field experienced by an individual atom within a dielectric material. Okay. So first we can consider figure. Here what I've shown is this is a dielectric material. Okay, now you can consider that this material is kept within an electric field. Okay, I have drawn two metal plates. I am giving a potential, positive potential here, a negative. So it is connected in such a way that this is connected to the positive cell of the battery, this is to the negative cell of the battery. Okay, negative side of the battery. Okay, now you see, when this plate is given a positive charge, obviously the charge separation within actually individual atom wise or individual molecule wise, you can say there is charge separation is taking place within the dielectric material. And finally we said that all the inside charges get cancelled and you get charges separated or collected on the surface of the dielectric material, which we call as the bound charges. Okay, so you here, since it is positive here, you get all the negative charges collected here. Since it is negative here, you get all the positive charges collected here. Okay, so now the field which you apply to the material, that is called as the E0. Okay, and that is actually the applied field. Okay, so E0 is the applied field. Okay, now because of this applied field, you know, charge separation takes place within the dielectric material, and there is actually a field which is existing due to the polarizing charge separation within the dielectric material, and that is called as the E1. Okay, because you know the direction of this is from here to here, this because this is positive and this is negative, you have a field applied in this direction. Okay, now within the dielectric material, charge separation takes place in the opposite direction as that of the applied field. This is positive here, this is negative here, so you will get a field applied in the opposite direction. Okay, you will get a field occurring within the dielectric material in the opposite direction, and that field is denoted here as E1, and we call this field as the depolarization field. Okay, so this is the depolarization field. Okay, now so this is in a direction opposite to the external field. Fine. Now thinking about we are going to, our attempt is to find the local field of an atom. Okay, so this method, how to find the local field of an atom, was actually explained, or it was introduced by Lorentz, and his idea to find this local field, his idea was that you consider a small cavity, a spherical cavity within the dielectric material, where this cavity contains the atom which we are bothered about. Okay, so here you consider here is a cavity here, and let me consider this as the atom which is kept at the middle, which it is denoted as a central dipole. So that atom, let us consider we are going to find the local field of an atom, of that atom. Okay, so you consider, with respect to that atom, you consider a spherical region near to it, very close to it. And this spherical cavity which you consider should be dimensionally sufficiently large compared to the dimension of the dipole. So compared to the dimension, it is a quite a large quantity. So but for the whole specimen, this is a small spherical cavity. Okay. So actually, the space outside the cavity can be seen as or treated as a continuous medium as far as the dipole is concerned, because for the dipole the whole medium is a very bulk thing, and the cavity is okay. So the medium outside the cavity can be considered as a continuous medium for the dipole concerned there. But the medium very close to the central dipole, okay, the medium very close, that is this region very close to the central dipole, which is inside the cavity, that can be considered as a discrete area, and the interaction with the neighboring dipoles can be treated microscopically. So for the dipole, the interaction between the immediate neighborhood, it is considered microscopically. Okay, so other fields are all macroscopic fields, and here the interaction between its neighbors is considered microscopically. So now the field Lorentz imagined within the dielectric material, and that cavity is called as the Lorentz Lorentz cavity or Lorentz sphere. So let me call this as the Lorentz sphere, and the field which is existing on the spherical surface is called as the Lorentz field. And you can see that on the surface, you can again see, because of the negative charges here on the surface as a whole, if you macroscopically if you look, actually you can say that positive charge is getting collected here because of the negative charges here, positive charges on this side of the sphere, and negative charges getting collected on the right side of the sphere because of the positive charges on the dielectric material. So if you look at the sphere, you can say that there is a charge separation collected on the surface of the sphere, and we call this and because of that an electric field will be experienced on the surface of the sphere, and we call that Lorentz field, and I've denoted here it as E2. Okay, so this field which is existing on the Lorentz sphere is called as the Lorentz field. Okay, and here it is denoted as E2. So it is because called as Lorentz field or Lorentz sphere because this idea was actually introduced by the scientist Lorentz. Okay, so this is all about the surface field on the surface of the sphere. Now what you have to consider is the field existing within the small microscopic area which is nearby this central dipole. Okay, so you can say that there are many dipoles existing very near to the central dipole or the atom which you consider, and there are very small interaction taking place within the spherical cavity. Okay, but then if it is spherically symmetric case, or if the crystal is a spherically symmetric, that is means it can be a cubic structure. If it is a cubic structure, then it will be spherically symmetric on either side. If with respect to the atom, the other atoms or neighboring atoms will be distributed uniformly. If that is the case, you can say if it is uniform charge or atom structure, the fields existing within the material may get cancelled. So that means if it is a cubic structure material, then the field inside the cavity, or it is not on the surface, it is inside the cavity, which we represent here as E3. It is not denoted here, E3, that can be considered equal to 0. So if it is a cubic site, you can say that this is equal to 0, otherwise not. But anyway, we have now found out that when a material or when an applied when an electric field is applied on a dielectric material, there is an applied electric field, there is a depolarization field E1, there is a Lorentz sphere or the Lorentz field E2, then the field within the Lorentz sphere, that is E3. So all these fields will be experienced by a dipole sitting at the center of the Lorentz sphere. So a dipole which is sitting here, that will experience the applied E0 electric field, the depolarization field, then the field on the surface of the Lorentz sphere, and that due to the interaction of the neighboring dipoles. Okay, so I can say that the local electric field denoted as E local is equal to E0 applied field, okay, plus depolarization field E1 plus Lorentz field E2 plus E3. Okay, and this field, that is E0 plus E1, which is the field existing on the bulk material, and this can be treated, or I call this effective field E0 plus E1 as E. Okay, so that is the bulk, that is the field, effective field appearing on the whole specimen, on the whole volume of the specimen, that is E0, and effective field that is due to the applied field and depolarization field, there will be a resultant field, because you know that E1 is acting in the opposite direction as that of the E0, so there will be a net resultant field, and that net resultant field let me call as E. Okay, then you have the E2 and then E3. Now I consider a cubic structure, so or a spherically symmetric structure, where you can say that E3 is equal to 0. Okay, so I don't consider this E3 as well. Now, so E local is actually E plus E2. Now, the E2, that is the Lorentz field, can be computed to be equal to P plus 3 by epsilon 0. That is E2 can be computed to be equal to polarization vector P divided by 3 epsilon 0. Okay. Now we are not going to derive that. The derivation is not required, but then you have to understand that this is equal to P by 3 epsilon 0, where P is the polarization vector. And what is polarization vector? It is dipole moment per unit volume. So I can write this E local or local electric field as equal to E plus P by 3 epsilon 0. So this is the final formulation or final formula for the local electric field of an atom. Now you see, this is interesting to see such a formula, because you know the field experienced by the locally by an atom is different from the field, effective field, which you experience on the whole specimen. Okay, effective field experience on the whole specimen is actually E, right? But then that field is different from the field experienced by an atom inside the dielectric. So locally, a dipole existing in the dielectric material experience a field more than the effective field E. Okay, so the total or the net resultant field E, so P, it will be increased by P by 3 epsilon 0 for an atom sitting in the dielectric material. That means the local field at an atom within the dielectric material is different from the field E, and this field E is called as the Maxwell's field. And I have shown here the atoms sitting at different lattice sites. So here one atom is there, here another atom is there, and another atom is there. Okay, now you see we are talking about the field experienced by this atom. Okay, now I've drawn here the electric field. Okay, let me say this is the x-axis. Okay, it is the electric field axis, or let this be the distance x direction. If you draw a plot, let me say this as the x-axis, that is the position of the lattice, and this is actually the electric field, the y direction. And here you can see the E is a field which is a constant field, right? So E doesn't have any variation because applied field E0 is same, it is not changing. Depolarization field E1 is not changing. So E is a constant field. That constant field is represented by a straight line. And you have this this P by 3 epsilon 0. This polarization vector actually changed depending upon in the crystal structure near to the atom, this polarization vector will be high, and away from the atom, obviously this polarization vector will be low. Okay, so that means depending upon the variation in the P by 3 epsilon 0, this E local can have a variation. So when you plot the E local electric field, it will be local electric field will vary like this, which means that near the lattice site, near the atom, local electric field will be very high, and away from that low. Away again near to the another atom, it will be high and low and high and low like that. Okay, so so what we understand that the field experienced by the molecular site is more effective, or it is more than the total effective applied Maxwell's field. Okay, so the molecules are more effectively polarized than they are under the average field. That is what it means. So we discussed about the local field of an atom. So we understood that local field is of an atom means the field experienced by an individual atom within the dielectric material, and that is different from the effective field of the applied and the depolarization field, and that is actually effectively more than the local field is more than the average field existing on the whole volume of the specimen. Okay, so this is all about local field of an atom. So if you have any queries, you can put it in the comment box. Thank you very much.